Alrighty, so the last part of lecture 1 here is to kind of wrap up the background and basic information about parametric curves and how to go from parametric to like rectangular or Cartesian, and what we can learn from both. So what I want to do in this video to wrap up here, is I would like to, remember in the last video we talked about how do you go from parametric coordinates to, or like parametric equations to the standard functions of x and y in rectangular coordinates or in Cartesian coordinates, right? So this time what we want to do is we want to go from a standard curve and define a parameterization. So let's go from like some curve, say y equals f of x, to parametric equations that represent this curve. To parametric equations. So I could say like x equals x of t, y equals y of t. Again, some bounds would have to be introduced, but right now what we're primarily focused on is actually changing from this curve expressed in terms of y as a function of x to this curve expressed as a parametric curve here. So there's always a nice, not maybe easy, but a simple parameterization that we can introduce. So this is, we can always do this. So we can introduce a parameterization as follows. We just simply let x of t equal t, and then y of t is, well, we're just replacing x with t now. So where we had f of x up here, y of t is just f of t. And then if this function, y equals f of x, was, say, on the interval a to b here, right? Like, again, maybe I'll draw it. We have some y equals f of x from a to b, right? Well, then if x and t are, we're just saying they're the same, well, then that gives us a nice parameterization here, or nice bounds for our parameterization, namely a and b. And so this is one way that that you can always define a parameterization of a curve, right? So we can just say, well, it's moving directly proportional to, like, the speed at which some particle is moving along this curve is directly proportional to how far you're going over in the x direction. That's what it means to say x of t equals t here. There's no restriction on us doing that. So here, let's do a quick little example. And it will kind of segue into some more topics. So for this example, let's say we have y equals 2x squared minus 3. Again, this could be on some interval. The domain of this function is all real numbers, so we could get away with doing like negative infinity to infinity, or we could assume it's just on some finite or some interval. So, but in either way, if we want to take this equation and express it as a parametric equation, well, what we just learned is we can just say, well, let's let x be t. Let's let y be f of t, right? So we just replaced x with t, so that's 2t squared minus 3. And that's a parameterization for this curve. And however, what I want to say from here is, like, this always works, right? And so that's good that we can take some function, some continuous function over an interval. We can say, well, like, let's let x of t be t, and then we just plug in t everywhere we saw an x, and then we're good to go. This is not necessarily unique, and sometimes it's advantageous, depending on setting or application, to define a different parameterization. So you can define multiple parameterizations of the same curve. I'll say multiple, abbreviate here, of the same curve. And one that is really common is when you define a parameterization like x of t equals t, and then y equals f of t, whatever it is, right? When we look at that curve, right, that's, you know, it's a parabola, y-intercept -3, right? It's pretty sketchy. That's not exactly what it would look like, but say we're close enough here. This is -3. And let's pick an interval here. Let's just say this is A all the way out here, and this is B all the way out here. Okay, and so we're looking at the parameterization just over this interval here. Maybe I'll indicate it in red. So we're just looking at the parameterization of a segment of this curve. Well, if we were to start at A, if we just let x be t, and we're going from the bounds A to B, that means we would start at A, and as we travel, we would end up at B. So you can almost define what's called an orientation of your curve, because we're traveling as t increases from A to B, we're traveling in a given direction here. So this gives an orientation of our curve. All right, sorry for the cut in video there. I had some recording and upload issues, so I lost a handful of footage there. So anyway, so we have an orientation of a curve, right? And we're saying that the standard orientation is usually given by just taking x equals t, or how about standard parameterization? By x equals t and then y equals f of t, right? And we're using the example here where y is 2x squared minus 3. And we can define a reverse orientation by taking the same curve, but we parameterize it in the opposite direction. Meaning here at time t equals a, you're at x of a, y of a. And here at t equals b, you're at x of b, y of b, like the point, right? But if we wanted to reverse the orientation or define a parameterization that flips how we travel along this curve, like instead of starting from A to B, we would go from B to A. Let's say, here, let me kind of B to A, right? But now what we want is we want that at time t equals A, we're over here. We're at the point x of B, y of B. And then we travel in this direction now, and we end up at time t equals b, we end up at the point x of a, y of a. And so we're going to have to define a different parameterization to do that. And here's how we can do that. We can let x of t now be a plus b minus t. Because we want to be at the x value b at time t equals a. So if we plug in a, we'll get a minus a, which cancels. So we just have x of t equals b, right? And then for y of t, well, it's just then our function, but now we plug in a plus b minus t. So this would be 2 times a plus b minus t squared minus 3. And so you can use this parameterization. This gets you the reverse parameterization. Whereas we could call this one like the standard, or forward if you'd like. And that's true in general, right? So in general, this would just be, like maybe I'll write the general case down here in orange, In general, it would be y of t equals your function, but it's evaluated at a plus b minus t. And so that's, this gives us a second or another type of parameterization for the same curve. And in fact, you can define multiple, maybe even an infinite number of parameterizations of one given curve. You just have to check restrictions on your domain, on the domain of your function. And here we see y equals 2x squared minus 3, the domain. This is well defined for all real numbers, right? So that means we're okay here to play around with some different types of parameterizations. So like one example we could have is we could let x of t, sorry, let's change back to a color that's a little better on a white background. So here we could have x of t. We could just pick something like, say like 3t minus 2. And then y of t would become 2 times 3t minus 2 squared minus 3. And this looks like a completely different parameterization, and it is a completely different parameterization, but it is indeed the same curve. It's describing the same curve. So it's just in what direction and how quickly you're traversing this curve is what the changing in parameters tells you. And so, you could simplify this to get, so we'd have like 2 times, if I square that, it would be 9t squared minus 12t plus 4, then minus 3. So this looks like we'd have 18t squared minus 24t plus 8. And then, so that would be, plus 8 minus 3. So how about plus 5? And so these x and y functions of t give us another parameterization for, again, same curve. And the orientation of this parameter will be, again, in this direction. But the speed at which you're traveling along this curve changes linearly as you change along the curve, right? And it changes by 3t minus 2. That's the describes how we're traversing this curve differently as we move from the starting point of our segment to the end point of our segment. Okay, and so kind of in general, there's not necessarily a unique way to take just a given function and parameterize it. There's many ways you can do it. The most standard and probably the most practical for most things we will be looking at is to just let x be t, and then you just sub in t for x in the equation for y. But again, sometimes it may be helpful to reverse our parameterization or look at a completely random one. Okay, and to wrap up our talk about parametric equations, I think there's just some neat examples that are worth going over. So here we have neat examples. The first one's called a cycloid. And I'll describe what a cycloid is. So let's imagine that we have a flat surface, and with my drawing, you're really gonna have to use your imagination. Let's try to make that a little better. I made it worse. Okay, you get the idea. So we have a flat surface, and let's say we have a wheel or a circle, and let's say this is a circle of radius a here. And we're standing over here, and we push the wheel, say we push it in this direction, so the wheel starts to spin like this, right? And we want to trace, so say this is a spoke of this wheel. Say we're gonna fix our attention to the end of one spoke here, and we're gonna look at just this point and see what happens to this point as the wheel spins. So if we give this wheel a push, after some amount of time, would be farther away from us, and this new spoke would now be down here because of how we pushed it, right? And so if we kept observing, what would happen? We would see the wheel goes like this, it would come back up, and you can start to get the picture, and eventually it would make one full rotation, right? But again, what we want to do is focus on the path that a fixed point of this wheel took as it spun. And if you trace out this path, you get something like this. And so, you know, if I were to go off screen in both directions, basically a cycloid looks something like this. It's the path that a fixed point on a wheel takes as the wheel is rolling. And the textbook has a really good explanation for the derivation of a parametric equation for this curve, for a curve that we call a cycloid. So if you're interested in how these are derived, then I would highly suggest taking a look in section 1.1 of the OpenStax textbook. And the parameterization for a cycloid for a circle of radius a is a times 1 minus sine t a times t minus cosine t. And this is our parameters bounded between 0 and 2 pi, since we're dealing with periodic motion here. So that's one pretty neat example of that's a little more involved, and you can see where it would show up in physics and stuff, is to look at the parameterization of cycloids. Okay, The next example that I wanted to show is called a hypocycloid. For a hypocycloid, let's imagine a circle of radius A again. And now let's imagine that there's a circle of radius B. Let's imagine the inside of this circle has Velcro. And this circle of radius B also has Velcro on it, and they're stuck here. So here's a circle of radius B. And we could push this circle. It could stick to the inside of the circle of radius A, and we could push it all the way around. And we want to look, let's say we push it in this direction. And we want to, again, take a fixed point on this wheel of radius B, and we want to trace out the path that this one particle takes. And so if we were to give this circle a push, and it were to stay along the inside, we would get something like this here, because as we push in this direction, the wheel is going to rotate this way, right? As the circle goes around the circle of radius A in this direction, the circle of radius B is turning in the opposite direction. And so we get something like this. Can do a few more here. Maybe I'll just draw a handful. Okay, and as we go around, this keeps spinning. It's still spinning in this direction. So maybe here it's straight down, and then it keeps spinning in that direction. Keep spinning. Keep spinning. Right? You know, and it depends on how fast it's going, but the end result looks something like this here. So and here my circle doesn't really match, but you know, again, it's just from a bad picture. You can kind of see here, it looks a lot better. It follows a lot better. And so this kind of diamond shape with these four cusps here, this curve is called a hypocycloid, and it's the result of the wheel of radius B spinning around the inside of the wheel of radius A. And these have a pretty complicated parameterization, which again, if you're interested in how these are derived, I would definitely take a look at section 1.1 of the OpenStax textbook, where it covers this. And so this is given by A minus B times cosine T plus B cosine A minus B over B times T. And y of t is given by A minus B sine T minus B sine A minus B over B times T. Again, it would be standard to consider this between T values of 0 and 2 pi. And so these are what we call hypocycloids. And there's one last example that, that I'd like to talk about, which is pretty cool. And these are called epitrochoids. Epitrochoids. okay? And it's similar to a hypocycloid here. But now what we do is we have a circle of radius A, and we take the circle of radius B to be on the outside, say like fastened to the outside of the circle of radius A. And then we give it a push, and we see what happens as we go around, right? And so you can see at first you get something like this maybe, and then you can try to see what would happen here. And if you're interested in this, I'm actually going to leave this as a little extra thing that I'd like you guys to take a look at here. So this homework problem is not assigned, but take a look at problem 58 from section 1.1. Again, it's in the OpenStax textbook where our homework is assigned out of. Again, this isn't an assigned homework problem, but I want you guys to take a look at it. And it's a pretty cool thought experiment. They give you the parameterizations for this kind of motion, and you should see if you can figure out what kind of shape this will make if you were to complete, say, one full rotation of the circle of radius B all the way around back to where it started. What is the epitrachoid going to look like? And I think that's, if you're interested, that I would absolutely check that out. Okay, so this wraps it up for the introduction to parametric equations. In the next set of lecture videos, we'll be looking at calculus of parametric equations, how we can use calculus of parametric equations to take derivatives, take integrals, find arc length, things like that. So in the next set of lecture videos, that's what we'll be talking about, and I will see you guys then.